Hey! So, returning to the topic of wood stoves, I'm going to talk about radiation and try to illustrate it as best I can so that you come out of here feeling comfortable with radiation, thermal radiation. Before I do that, let me respond to a question that came in last time, which is what actually is fire? So in the wood stove, you know that you put wood in there, you ignite it, and I talked a little bit about you need an activation energy, which comes from the ignition process, the heating it to get it started. And then you get this ongoing chemical reaction process that's happening, which burns the wood. It reacts it chemically with the wood, with the oxygen in the air. The molecules rearrange, and you come out with mostly water and carbon dioxide. But just to follow up on the questions, like, so what actually is fire? I mean, at the most basic level, it's these chemical reactions that are releasing chemical potential energy as thermal energy. But you're used to actually seeing the fire. It's got a structure. One of the questions on the problem set that was just due was also talking about the fire in a candle. How is that structured? And I will point out that the structure of a candle is structured. It comes about in part because of buoyancy. It's convection. The fact that you have the chemical reaction going around the wick of the candle, and I'll talk more about the flame, means you've got hot gas there, actually very hot gas. It's at atmospheric pressure because it's not enclosed by anything. It can't be different in pressure by much from the surrounding air, otherwise the air would accelerate. The gases would accelerate. So it's atmospheric pressure, it's hot. A hot gas at atmospheric pressure doesn't have very many molecules per cubic inch. So it's low density. And therefore, it's lighter than the buoyant force on it, and up it goes. And so that rising of the heated gases around a candle flame pulls the flame out into this elongated shape that goes off into the sky. Well, I mean, it goes up and then eventually you stop seeing it, but the hot air is still there. If you put your hand over a candle, you can feel the heat rising to your hand in the form of hot air, convection, for quite a distance. The flame itself, so what are you seeing? You're actually seeing thermal radiation. The flame has chemical reactions going on among the gas molecules and little particles that are in the flame as well. And those chemical reactions that are taking place in the gas release, some of it is simply thermal energy, but some of it is visible light energy. So it's coming off as electromagnetic waves, which are visible to your eyes. So particularly when the chemicals are very simple and they react perfectly, are very cleanly, you get very specific. The look is specific. Like I'm thinking of a gas burner. If I just light the gas burner here, I guess I have something to talk about here. Let me pull a burner out and just. You can barely see it. It's a roaring flame going on here. Lots of thermal energy being released by a reaction between natural gas and air. But the reaction's pretty clean and simple between gas molecules, gaseous natural gas and oxygen. And the reactions emit mostly a blue color, which my background is actually in optical, atomic, and molecular physics, so I should be able to tell you the blue color. I think it's known as the swan bands of carbon. It's thermal radiation, but it has a particular color because of the molecules that are involved in the reaction. Occasionally you see an orange flame show up in it. And that orange flame has little particles of carbon in it that are super hot. They're very, very hot, and they emit thermal radiation characteristic of their temperature. And that's the orange glow. So the vertical shape to it is created by buoyancy and the convective rising of heated gases that have very low density. The various glowing things you're seeing are thermal radiation. Some of it is simply temperature-based, which is the orange glows that you see occasionally, and some of it is filtered in effect by the molecules themselves. They have specific colors they like to emit. And you're familiar with a specific color story when you go to fireworks. When you watch the fireworks glow red or green or something like that, they're using the atoms and molecules in the fireworks to emit thermal radiation, but where it's been filtered so it's very specific, characteristic of the atoms and molecules themselves. Okay, so in a wood flame, lots of that glow, that thermal glow from the particles in the flame itself. Wood, if you've ever baked wood in an environment that doesn't have any air around it, so for example, I used to put wood inside aluminum foil and poke a little hole in it, and you bake the wood in that aluminum foil. There's no air in there, so it would emit gas. Various gases would bake out of it. They'd come out the little hole and they would ignite. And so you would have a jet of burning gas coming out of the little hole, which is lots of fun because kids like to play with fire, and I was at least like everybody else. When you were all done, what was inside the aluminum foil? Charcoal. That's how they make charcoal. They take ordinary wood, they bake it in the absence of air, drive out, a lot of chemicals come off as gas that is itself flammable and burns with an orange flame and stuff. It's the flame that you're used to seeing in a fire. And when you're all done, all that's left is this black charcoal, which does not burn with the flame anymore. If you burn charcoal, it just glows right there. There's nothing to become gaseous left. And so the glow is right there in the charcoal. The gases are gone, so there's no flame around it where the gas is burning in the midst of the open air. So got some detailed questions here that are, okay. So you okay with the basic idea of a flame? Where the flame comes from, this chemical reaction is actually occurring in the gas phase. Gas and gas reacting, emitting light. Charcoal doesn't do that because it doesn't make any gases. The question that's coming in here is one of the problem set questions where suppose you all are sitting there and you actually are, all of you, consuming about 100 watts. You're consuming about 100 joules of chemical potential energy every second, which is 100 watts. You are actually a 100 watt mechanism that just consumes 100 watts all day, all day, all day. You can go above that, but it's hard to go below it. And what happens to the 100 watts? It becomes thermal energy with very rare exceptions. So you're actually emitters of 100 watts of thermal power most of the time. This, incidentally, is why when you go into an auditorium or a theater or something like that that's empty and it's been chilled down so it feels uncomfortably cold, you go in there and once all the crowd shows up, it stops being so cold because you're all individually about a 100 watt little space heater. And if there are 1,000 of you in the theater, that's 100,000 watts of heating power. That's a lot of space heaters. You know, the normal space heaters that you buy and plug into a wall and they just sit there glowing and toasty warm and all that, those are like 1,000 watts. So imagine having 100 of them in an auditorium. It adds up. And you've probably noticed that when it gets a crowded room can become very hot. If we put you in an environment where you lose more than 100 watts per second, so you're making 100 watts per second and you're losing more than that, you're going to start running a deficit of thermal energy. There's 100 watts in, 200 watts, say, out. You're losing thermal energy. And your temperature is going to go down and down and down. And a couple things can happen. You can start shivering, which is the natural way in which you burn even more chemical potential energy per second and try to replace the energy you're losing. Or you actually do get colder. Or you wrap yourself up in something that prevents you from losing 200 watts of thermal power. You okay with the idea of when I talk about a watt and power as opposed to energy? Do you all understand that? Or how many secretly would like to hear me talk about the difference between energy and power? Okay, good, okay. So energy, the answer is yes, people would like to hear about it. Energy is the specific amount. It's like how much money you've got. So they're conserved quantities. You have $100. That's equivalent to having 100 joules of energy, just in the analogy. If you start giving away $1 a day to every time you go buy the charity bin, you put $1 in it. So you're putting in $1 per day. That's a steady flow of money out. And maybe your salary is coming in at $2 a day. Okay, so you're gradually accumulating more energy. This process of passing off money steadily is analogous not to energy, but to power. So go back, let me go over to the world of energy and set aside the analogy. If you have, say you've got a store of 100,000 joules of energy in your storehouse, and you give out 100 joules of energy every second, that we measure that steady passage of energy over a course of time. We call that power. How much energy you can deliver per second. The more powerful you are, say, as to put it in the context of an athlete, if you are capable of doing 500 joules of work every second, which is that's a lot of work per second. That would be, you're capable of generating and passing off 500 joules per second. That's 500 watts. And that's pushing the limits of what a person can do. Is that true? Yeah, if you've ever ridden, for example, stationary bicycles, sometimes we'll report to you how many watts of work you're doing. How much watts of power, how much mechanical energy you're passing off per second. And if you get up into the 500 watt range, you're really working hard. People could probably go up into the 1,000 or 2,000, but briefly. It's just enormous amount of work done in a second. So power, you often consume power. You consume this quantity we know as energy in the form of power. You're using it steadily day after day after day, hour after hour. So light bulbs, for example, are rated in how much power they use. That's how much energy per second they use. You pay for this stuff, this energy type stuff, finally in the total amount of joules you consume. So if you've got a light bulb that is a 100 watt light bulb, meaning that it consumes 100 joules of energy every second, and you run that for an hour, that's 3,600 seconds, you will have used the product of the two. 100 joules per second times 3,600 seconds, which is 360,000 joules. The seconds cancel out. The time times a per time, the time cancels. So you're at 30, is that right? 360,000 joules, and that has a certain price when you buy it from the electric company. The electric company usually sells electricity in what's known as kilowatt hours. A kilowatt hour is the equivalent of consuming a kilowatt all day, and a kilowatt, 1,000 joules every second, times an hour. So 1,000 joules every second times an hour is 3.6 million joules. Yes, 3.6 million joules. So 3.6 million joules probably costs you about 5 or 10 cents. So what I would describe a moment ago, which was 1/10 that, probably would cost you about 1 penny or half a penny. Okay? I hope I've made some progress on the idea of power. It's just energy per time. All right? the body heat example, if everyone wore parkas or perfectly insulated clothing, would the room's temperature not increase because the heat is kept in the person? Yes. If you all are producing about 100 watts of thermal power, that is 100 joules every second, and we're assuming that you send it all out into the room. You don't accumulate any of it. And that's the normal steady state situation. Suppose you've been in this room for a week. If you had been making more thermal energy than you had been sending out in the room, you would have been accumulating it. And your temperature would have gone up and up and up and up. And after a week, this is not intolerable. So I can guarantee you will not have accumulated it the whole week. You will have gone into this steady state process where you're making it and releasing it at the same rate. On the other hand, if you send it off faster than you're making it, you're going to get colder and colder. And again, after a week, this is going to be a big problem. So the reason I have you sit in here for a week is because we're just guaranteeing that you just can't not send it out at the same rate you're making it. Is that okay so far? So if we now wrap you up all in parkas and stuff like that, what we're doing is effectively stopping you from sending your heat out. So you're making it, but it's not going out into the room. So the room will not be getting warmer. Another person walking in the room will go, oh, you know, it's nice in here, it's not getting warmer. But you'll be getting more and more and more uncomfortable because you will be making thermal energy unavoidably and not getting rid of it. So you're accumulating it. And what will that do? You get hotter and hotter. And you know this from experience. You know what happens if you do that. You're wearing too many clothes in some room and you feel uncomfortable. You start taking off the parka. It's just automatic to you, but this is just the physics of something you do naturally. If you're overdressed, you take it off. If you're underdressed, you start putting it on. You can feel the drift of your body temperature up or down. Your body tries to regulate temperature very carefully, and it starts basically screaming at you if the temperature is going to go too high or too low. And you have behaviors that fix the problem. And they're just hardwired automatic in you. It's hard to defeat them. All right? All right, so what I do want to then talk about thermal radiation and try to get it across to you so that you're really comfortable with it. I've talked about making the thermal energy at length. I've talked about how to send it by conduction. I've talked about how to send it by convection, whether the convection is natural, that involves buoyancy, or force, that involves a fan. Thermal radiation is the other way to send heat around, and it's the more mysterious of the bunch. And as I quipped the other day, the whole idea of what's radiation, it's a catch-all word in physics or science. Anything that's moving is radiation. So when they say, oh, you're exposed to radiation, we don't know whether that's dangerous or not. I'm currently exposed to lots of radiation. The light coming down and that you see me by is radiation. So anyway, there are radiations that are dangerous, there are ones that are not dangerous, but it's just stuff. And the thermal radiation that comes off of objects that have a temperature other than absolute zero is electromagnetic radiation. And so it's light and all of light's siblings. And the details about that radiation. First off, the origin of it I mentioned last time, I'll mention again, is the thermal jiggling. That an object with thermal energy, its particles are jiggling around statistically. I would say, randomly with sort of important statistics that govern how the energy is distributed. But they're jiggling around, and many of them are electrically charged. And electrically charged particles or objects that accelerate emit electromagnetic waves. It just comes with the territory. It's a topic beyond the semester, but it's there. And so a hot object, and again, hot is any temperature other than absolute zero, emits thermal radiation. Off go the waves. Its emission is characteristic of its temperature and to some extent its color, and I'll talk about color in a minute. But the temperature is the key thing. the colder it is, the more its thermal radiation shifts towards what are technically long wavelength, low frequency waves. The waves of, for example, radio waves. And so very cold objects emit mostly radio waves. And very cold is like crazy cold, like a few Kelvin. As you go up in temperature, the spectrum of the thermal radiation begins to shift to shorter wavelengths, higher frequencies. It goes out of the radio waves and into the microwaves or across the microwaves. Go hotter still, it gets into the infrared. Hotter still, it finally begins to drift into the edge of the visible spectrum, at the red edge. And so you've seen this your whole life too. You get things hot. As they get hotter, they go from being looking normal to, oh my gosh, it's glowing a little bit red. That means it's gotten hot enough that it has a little bit of its thermal radiation at the edge of the visible spectrum on the red end of the rainbow. As you go hotter still, it begins to drift more into the yellows and oranges, yellows, greens, ultimately towards the blues. And the spectrum shifts and it goes up until finally, and because it's a mishmash, it's not a specific rainbow color, it's across the colors, and your eyes, for interesting reasons, see them as mixtures, or the pastel mixtures of colors. They start to drift into what we identify as white, the yellows and into the yellow-white, and then white, like the sun. And then if you keep on going, you start going to the ultraviolet and farther. But the sun is a beautiful example of something that's very hot. It's hot enough that its thermal spectrum is heavily distributed across the visible part of our stuff, the stuff we can see. And it's a mishmash of colors, and the mixture is just right that we perceive it as white. It's not, it includes red, yeah, it includes some stuff that's specifically blue and stuff that's green, but you bring them together and you mix them with the right balance, and we see that as white. So the sunlight that you live in, under, that's thermal radiation. It's the sun's thermal radiation, and it's emitted in the visible because the sun is so hot. If the sun were cooler by half the temperature or something like that, it wouldn't be white anymore. It would have shifted far enough toward the red end of the spectrum, with radio way out in the distance, that it would start to look red-orange and stuff. And so those of you who have studied astronomy or paid any attention to it, there are other stars out there that have different distributions of thermal radiation because they're different temperatures. If they're cooler, they're redder stars. And if they're hotter, they're actually bluer stars. Our sun is just, it is what it is, and it gives us nice white. Okay? So first observation then is that the temperature of the object determines essentially its spread of wavelengths, or alternatively viewed frequencies, which I don't really want to go into this semester unless you want me to. They shift out of the radio waves to the microwaves, across infrareds into the visibles, and so on. Second observation about the thermal radiation is that the thermal radiation coming off of a surface, and pick a specific surface, this much, the amount of thermal power that comes off it, again, measured in watts if we like, which is energy per second, scales as the fourth power of the absolute temperature. So if you take as the temperature is going up, not only are the colors shifting, or the distribution of the spectrum, but the brightness is changing, and it's changing fast. An object that's really cold, that emits mostly radio waves and microwaves, is also extremely dim, barely emitting anything. By the time you get up into like room temperature stuff, the emission is now, for a surface like this, now you can measure it in watts. Back when it was down to a few Kelvin, you'd measure it in like millionths or billionths of a watt. Now you're in watts. And if you start getting up toward the sun, a surface like this would probably emit kilowatts or even megawatts. There's a tremendous amount of thermal power coming off. So the brightness goes up really fast with temperature. Okay? Last thing I think to talk about with this, the importance of color. A surface's ability to emit thermal radiation has to do with whether it's the particles jiggling around it are whether they're electrically charged, are they jiggling correctly to emit thermal radiation? And some surfaces are and some surfaces aren't very good. Some are good at it, some are poor at it. It turns out that a surface's ability to emit thermal radiation is the same as its ability to absorb that same thermal radiation. Many of the concepts in physics, the principles in physics, work the same forward in time as they do backward in time. Where things don't reverse easily in time, I'll come back to, is when the reversal has statistical problems and you get this loss of order going forward in time. You don't get the recreation of order. You can't run the thing backwards. Let me try to flesh this out better. The laws of motion, or the collisions between two very simple objects that can't waste energy, the collisions between my two fists, suppose there are two atoms, the collision like this, if we film it, it looks like this, boing, okay? If you run the movie backwards, it looks like this. And the law of physics looks the same going forward in time as it does backward in time. This kind of a simple collision between two systems that can't waste energy, they're the same. Time doesn't care about, the direction of time doesn't matter. The collision looks the same forward as it does backward. The laws of motion, two bumper cars, they do this stuff, two perfect bumper cars. This is forward in time, and if you run it backwards, it looks like that. You would look at the movie and you'd say, well, that looks fine. You look at the movie backwards, it looks fine. It looks the same as forward. The point of all this is there are lots of things in physics where if it works like that forward in time, it also works like that backward in time. It looks the same. And why am I doing this? This harangue is about if a surface is good at emitting red light as its thermal radiation, it's also good at absorbing red light, that same thermal radiation. It's the movie run backwards. It looks the same. The jiggling motion in the particles launched a bit of red light. That looks great. Take that piece of red light, send it right back where it came, and the particles will absorb it. And it worked fine. The point being that, objects that are good at emitting a certain thermal radiation are also good at absorbing thermal radiation. Why tell you this? What is the best thing there is for absorbing light? What color absorbs light the best? Black, right? A black surface is the concept of a black surface is one that absorbs light perfectly. So, if a surface is capable of absorbing black light, how to do this? Let's focus on visible light as the thermal radiation we're dealing with. The sun's thermal radiation. A surface that you look at and you say, this is a black surface, jet black. That assessment, what you say when you look at that surface is you say, it's super good at absorbing the thermal radiation from the sun. The sun's light hits it and nothing comes back off. It hit and this is as opposed to what? As opposed to a mirror, or which reflects it perfectly. Or white, which reflects it but loses direction information. So the light comes off but goes every which way and you can't see where the light came from. You no longer see an image, for example, of the sun. In a mirror, you see the sun reflected. In white, you don't see the sun anymore. It's scrambled, but it's still reflected. And the other thing is transparent. So a piece of glass, the light just goes right through and you don't see it come off, apart from some little reflection, which I'll neglect. So a black surface is wonderful at absorbing the visible light from the sun. Put into sort of physics-y language, that means that black surface is ideally good at absorbing thermal radiation from a almost 6,000 Kelvin surface. Really hot, the sun. If you took that same surface and heated it to 6,000 Kelvin, it would be extremely good at emitting 6,000 Kelvin thermal radiations. if it's good at absorbing it, it's good at emitting it. That's the point. The scale on which this ability to absorb and emit thermal radiation is a 0 to 1 scale, and the quantity is known as emissivity. So a black surface, one that you look at with your eyeballs and say, ah, that's black, it has an emissivity of 1, perfect for thermal radiation of the type the sun emits, which is of a 6,000 Kelvin surface. I realize this is complicated, and I hope that you get it. Is electromagnetic radiation the same as thermal radiation? Thermal radiation is a subset of electromagnetic radiation. You can make electromagnetic radiation in more than one way. You can make it with a hot object. So if I heat up my black surface to 6,000 Kelvin, it will glow just like the sun with thermal radiation, which is, in fact, electromagnetic radiation. The reason that those are not equivalent is because these lights, which are light-emitting diode-based, they're LED-based, they're emitting light for a different reason. They're not making thermal radiation. They're assembling the electromagnetic waves more cleverly than that. So the light is not thermal radiation, it's characteristic of the temperature. Thermal radiation is characteristic of the temperature of the surface. So you in effect can measure how hot the surface is by looking at its thermal radiation. And I'm going to talk a few more seconds, or maybe a minute or two, and then I'm going to start doing the demonstration, because otherwise, it's boring. So thermal radiation is characteristic of the temperature. We know that both in the spectrum, and we know that in the brightness to some extent, and the color does matter. So a surface that's terrible at emitting thermal radiation will be relatively dim and have emissivity of 0-ish. And a surface that's very good at emitting thermal radiation, it will have an emissivity approaching 1. All right? The complexity comes about in that when you say the emissivity of the surface is 1, you have to specify the temperature at which that's true. A surface that looks visibly black to your eye, so this is pretty much black. This would have an emissivity of 1 for sunlight temperature light, for sun temperature, at the temperature of the sun. It's extremely good at absorbing the sunlight. It would be extremely good at emitting sunlight if it were hot enough. Okay? What we can't tell is it's not the temperature of the sun. It's at the temperature of basically the room, which is a factor of 20 lower on an absolute scale. How good is it at emitting and absorbing thermal radiation of a object that's at room temperature? And that we don't know, because looking at it, you can't tell. Is it good at absorbing or emitting thermal radiation in the infrared? Your eyes don't see it, so you don't have any sensitivity to it. You can't tell what surfaces are good at emitting thermal radiation in the infrared and which ones are, and equivalently absorbing it. It's a mystery. How to ask this as a question? A visibly black object we know it's going to be excellent for dealing with sunlight. It absorbs sunlight. If you get it hot enough, it's going to emit sunlight beautifully. In the infrared, though, at room temperatures, the temperatures of you don't emit visible light. The objects in this room, nothing here emits visible light as its thermal radiation. We're not hot enough. So we're playing back and forth with infrared light, and we can't see it. Therefore, we can't tell how good all the surfaces are at emitting it and absorbing it. I think I said that pretty cleanly. All right? What do you do? Well, the first thing I'll do before I start showing you is I will tell you that most surfaces are surprisingly good at absorbing and emitting infrared light. We can't see it with our eyes, but almost everything in this room is essentially jet black in the infrared. You send infrared light out, boom, it's gone. If you get it to room temperature, which is easy, you're emitting thermal radiation basically as brightly as you can for your temperature. So that is the case. Okay, so having talked this to death, let me show you thermal radiation in a couple ways. First, before I forget too far, these are little gadgets that see thermal radiation and can measure temperature by looking at it. They do take into account they do assume that they're looking at a surface that's pretty much perfectly good at emitting its thermal radiation. That it's got an emissivity of almost 1. It's basically, everything's jet black in the infrared. So you just press the button, point it at something and press the button and let go, and you can see what the temperature was. So I'll just send them around. When you're all done, somebody drop them off at my desk. But they're nice little toys. There are lots of these things around. You should know they exist, these gadgets that will see, they can measure temperature by looking at thermal radiation. So you can shine it at things that are cold, you can shine it at, in your head or something like that and see things that are hot. All right? What I have here, okay, so now having, again, talked it to death, I'm going to show you the view through this camera, which is a infrared, thermal infrared camera. There it is. Okay. First off, the heat ducts are over here. There's one of the heat ducts over there in the room. Can you see it? Can you see the heat coming off of it? It is hot. The lights overhead actually are warm, so they glow. They show up here in, this is all false color. They're showing in red, but you can see people here, right? And what this is telling you is how brightly things are glowing in the infrared. And what the temperatures are. You can see faces glow the brightest because these are exposed surfaces that are warmer than their environment. Yes, you guys are all really hot. Okay? And you can see things that are relatively cold. That camera up there, that's a camera. It's no evidence that it's glowing at all, but it is hotter than anything else on the wall. Probably because it's consuming electricity. All right? It's interesting. You can see not only are the ducts hot, but you can see the convection coming off them, heating the higher parts of the wall. Okay? So I guess, this is a great gadget. Alas, these are quite expensive, these gadgets. They have to have semiconductor devices in there that are sensitive to light you cannot see with your eyes, and do it in a way that's got optical resolution. You can see details. Okay, so you're all right with this idea that you all actually are glowing with thermal radiation. You're very good at it because, it's one of these. Diversity and inclusion is all the thing right now, and I can say that you are all the same in the infrared. It's like we're, one world, kumbaya, and all that. Everybody is basically jet black in the infrared. Okay? I told you that almost everything is jet black in the infrared. There are exceptions, and the exceptions include things like shiny things, or a thing that is truly white. White things are very rare. If you look at this, you will not see things that just sort of drop out as emitting no thermal radiation, because even though you may be wearing a white shirt, it's not white in the infrared. Basically everything's black. Are there exceptions? Yeah. Here's an exception. So this is a piece of mirror, broken piece, alas. And the reason I got this one is because this one has no protective coating on the mirror surface. The mirror surface is just bare metal. So this has a glass side and it has a metal side. And watch what happens. I got to figure out which one's which. This is the metal. This is glass. If we look at the metal, I've had trouble doing this before class. I'm going to hold the metal out. It actually works best if I look at myself. Where's me? There we are. Okay, there's me. You're seeing a reflection. You're not seeing the temperature of the mirror. You're seeing a reflection of me in the mirror, right? So the mirror does not tell you its temperature. It's terrible at emitting and absorbing light in the infrared. And as a result, it shows you reflections only. Not its own thermal radiation, but rather the thermal radiation that bounced off of it. So, is you okay so far? The other surface of this mirror, it looks shiny and all to your eyes, but it's through glass. This is the bare metal surface. the other surface isn't bare metal anymore. We're going to look through the glass and watch what happens. I'm still visible, but not so much anymore. Why? Because the glass, it's not black, but it's pretty hard to see through. It's showing you a lot of its own temperature. And actually, I could probably heat some of the glass up with my hand. Okay, and we might be able to see the glass glowing there. Yep. Can you see the glass has, it's blue on the right, left, yellow, orange on the left? I heated it up. It's showing you its temperature. Okay? So the point is almost everything is black, even windows. Windows don't, I'll stop this because it's, can I stop out? Windows don't let room temperature thermal radiation through very well. And as a result, when the temperature that's coming, the windows absorb and radiate thermal radiation just fine, even though they look transparent. They're not that way. They're just black surfaces pretty much in your house for thermal radiation at ordinary temperatures. Is that okay? So everything's glowing. Almost everything you encounter is glowing with its own thermal radiation and is also very good at absorbing everybody else's thermal radiation. So you're all playing exchange thermal radiation with everything around you. And if you come into proximity of something that is hotter than you are, in all likelihood, you will send thermal radiation at it. It will send thermal radiation at you, but that will be brighter. So it will send, there will be a net transfer of thermal radiation to you when you stand near something warmer than you are. The opposite if you stand near something colder than you are. And this happens frequently. For example, I mentioned the outdoor heaters at restaurants and stuff, which are often these domed things with a burner going underneath it, like an umbrella with a burner, or a column with glass around a flame, so you see this lovely flame dancing in there. That column of glass, remember, is black in the infrared. So it's heated by the flame, it's glowing like crazy. It's emitting thermal radiation like crazy. When you stand near it, you're not touching it, so you're not getting heat by conduction, and the air is a terrible conductor. And you're not above it, so you're not getting heat by convection. But you feel hot. It's thermal radiation. It's glowing like crazy. That gadget could see it. The little temperature widgets I'm sending around can see it. And therefore, you feel warm because it's glowing more brightly by far than you are back at it. So there's a net flow towards you, and you can play games like you can block it with your hands and stuff, or hold up a sheet of paper even to block the thermal radiation. It's all there. Another case of thermal radiation, before I go too far and don't do it, is up here, Ox West. Is this it? Where is this? Ox. How do we do this? I'm not sure. West HDMI. Is it there? It's not there. Camera. Aux. Oh, it's Aux East. I'm sorry, guys. Please. Okay, I can show you the demo anyway. What I want to do is, there's a match over here has been painted black so that it's very good at emitting and absorbing thermal radiation, like sunlight thermal radiation. If it were heated up as hot as the sun, it would glow brightly. If it's exposed to the sun, it absorbs brightly. Well, and we're going to send thermal radiation at it, not from the sun, but from a local very hot object, which is this light bulb over here. So this thing's going to get very hot. It's an old-fashioned, Edison-style light bulb. It's going to send its thermal radiation with the help of these reflecting surfaces, which again, they're reflective, particularly reflective in the visible. You can see them reflect. They won't show you their thermal radiation. They'll show you reflections of other people's thermal radiation. So I'm going to send the thermal radiation across the room. This gets very bright, so sorry about that. Here goes. And the question is when we lit it. Ideally, if I had that camera going and we'd see it light. Have I lit it? Well, I'll go over here and check. It's so dazzling, it's hard to see it. There's the thermal radiation right there. It's smoking. I'm trying to get the... Sometimes I've toasted marshmallows using this too. There we go. The match lit. So we sent thermal radiation from one hot surface to a colder surface. There's a net exchange. There's a net flow of heat from this guy to that guy, and it lit the match. You okay with that? Yeah. What color is the mirror? If it's, again, the mirror, the issue is it reflective in the spectrum of the thermal radiation you have in mind? And if it is reflective at that rate, for that thermal radiation, it doesn't have a color. Effectively, it just shows you reflections of whatever's out elsewhere. And I can show you that also. Remember, this gadget is also seeing thermal radiation. Right now it's seeing thermal radiation from a black surface, which is super good at emitting thermal radiation. It's not only black in the visible, it's black in the infrared. So it's really good at thermal radiation. There you see. This surface over here is shiny. And it's shiny not only for the visible, it's shiny for the infrared. And watch. It's not very good at emitting thermal radiation any more than it is absorbing thermal radiation at room temperature. This surface is misleading. Well, this one's, this is white. This is white. White's also not very good at emitting and absorbing thermal radiation. But the one kooky one is this one, which is painted white. And it's painted white, so your eyeballs say, oh, it reflects thermal radiation, albeit not in a randomly, so that you lose the mirror look. But white in principle just sends the thermal radiation back in cockeyed directions. But it's not white in the infrared. It's black in the infrared, which is the wacky thing. It's actually glowing very brightly in the infrared. So a takeaway for this, if you can wrap your head around it, is that what they look like in the visible doesn't give you a really good idea of what they look like in the infrared, which is where all the room temperature thermal radiation is being exchanged. Most things are black. The exceptions are the shiny stuff. The bare metals are shining up. And this, just put this, finish it with something useful to you all apart from aluminum foil. Why do you wrap stuff in aluminum foil frequently? Apart from that it's a convenient, like food storage enclosure, it's also terrible at emitting and absorbing thermal radiation. So if you want to keep something cold in an environment that's rich with thermal radiation, put aluminum around it. The aluminum reflects that incoming thermal radiation right back at the source. So it doesn't get into the food, doesn't heat the food up. Alternatively, you got a hot potato and you don't want it to cool off in the room by emitting thermal radiation, losing heat that way. So wrap it in aluminum foil. You now have made it very bad at emitting thermal radiation. So yeah, it's hot, but it's crummy at showing it to the world around it. So aluminum foil is just basically is a form of insulator against thermal radiation. And to put it in a specific context of recent memory, the firefighters, the people that go out there and deal with the California burning stuff, right? They carry with them an emergency tent. And the emergency tent is designed to try to minimize thermal exchange by conduction, convection, and radiation. By conduction, they wipe out the surface down to bare dirt. Get rid of the shrubbery, basically. They go down low, and they put the tent over them, and it's an aluminum tent, basically aluminum tent, and they don't touch it. So they want to get it over them, but not be in contact with it. So they're getting rid of conduction. They're down low, they're the lowest thing around, so that heat can't get to them by convection, because convection naturally lifts the heat up. If they're the lowest thing in the story, it's not going to convect down to them. And finally, they're a shiny metal. So the exchange of heat by radiation in and out, I mean, they don't care about radiating heat out. They do care about radiating heat in. They reflect it back. And so it's not ideal, but in the case of emergency, it's better than nothing. And people survive the fires by hiding out in these tents as the fire burns over them, whereas they wouldn't without it. So, okay, I'll stop, and more on Friday.